Here I am again. Good afternoon. For me, it's a pleasure to be here again. And again, I am Jaime da Riba Macedo, and I am the chair of Study Committee C2 of SIGRE. And this will be our second tutorial during this afternoon. Bad news for the presenters, because we had a great tutorial with Mr. Franco Crisi as the first one. So now you are challenged to make it better than the first, okay? But just to be different, there will be four presenters, okay? They will split the presentation in four parts, and they will divide this in four parts. And they asked us to make questions and answers after each part, a small part of questions and answers. So be prepared to make a lot of difficult questions. Well, for this second tutorial, that will be about restoration in the new situation of the electrical system. Again, it's a tutorial based in the work of a working group of Study Committee C2. And I think that the technical brochure was published last month. A brand new material for you in eSIGRE, available for you in eSIGRE. And today you have the opportunity to hear about this live with our four presenters that I will introduce now before I give you the floor, Mr. Babak. The first presenter will be Mr. Babak Badrzadeh, and he's currently a technical director, power system with Auricon, an adjunct professor with Monash University, a distinguished lecturer with IEEE PAS, associate editor of IEEE Power and Engineering Magazine, and Australian panel converter for SIGRE Study Committee C4. Unfortunately, I prefer to hear this about C2, but it's okay. No problem with Marta and you. Okay. The second presenter will be Ms. Cheryl Noronha. She's a principal engineer grid control planning with PowerLink Queensland. And a lot of more information about that I will not read this time, okay? The third one will be Mr. Lalin Kotalawala. He has more than 20 years of experience in different areas of power system applications, including power generation, control, and simulation. And the last, not the least, Mr. Vikas Singhvi. He's a program manager of EPRI's Transmission Operations Research with over 13 years of industry experience in transmission and distribution operations and planning. So I'm now confident that we will have a great, I don't know if it will be better or not than the first, but for sure, we will have a great experience now. Mr. Babak, you will be the first. The floor is yours. Thank you very much.
Hi, good afternoon, everyone, and thank you for the introduction, Jaime. You mentioned about one bad news, which we had previously. One good tutorial. Maybe the second bad news is that I don't think I'm going to be as entertaining as you are. So people need to either leave the room or wait until your 2024 presentation. Okay, all right. So for today, like Jaime mentioned, we were sort of fortunate that this technical brochure was published like around 10 days ago, so it's already available. I'm not sure if many of you have seen or read it. So obviously this is a 110 minutes tutorial, and obviously we are allocating at least 30-40 minutes for your questions, and so that we can answer your questions. So needless to say that we're not going to, unfortunately, cover everything that was presented in this technical brochure. And as you can see here, this is, to my experience, this was my third working group that I convened. So we had 25 members from 15 countries. So 25 is quite a big number, basically. Typically, we have a higher number and most people disappear, but 25 is a quite good number. What I'm trying to highlight here is that, and unlike some other tutorials, we try to include people that already here present. Fortunately, I managed to convert another 3 people that already in Cairns. So it's only 4 of us trying our best to represent 25 people. So we may not be able to represent everything that, all the great work that was done in this technical brochure, but we'll try our best to basically discuss with you and share some of our understanding of the salient point. Okay, so what are the drivers for this work? There has been a lot of great work by SIGRE and other organizations on publishing technical brochures and other documents on various aspects of system restoration. So what are we trying to achieve here, and to making sure that we are not repeating or contradicting all the great work that has been done to date. Our key focus area was to reflect on energy transition and on the rapid change in energy mix that we have been seeing in different countries, basically. And recognizing that we have been discussing a lot, and we have, for example, 6 great sessions in C4, and we have many more in C2 and others during these 4 days that we are here. And the vast majority of these discussions on operation of IBR and their performance during system normal. And surely these are extremely challenging as we have moved to a system with higher share of inverter-based resources. But to make it even worse is that if you thought these are complex, as we get to system restoration and involving some IBR, and we are not still talking about the system with 100% IBR, just involving IBR makes those dynamics and interactions more complete than whatever else that we are talking and what you are going to listen in other sessions. So that was the key value proposition, to make sure that we are reflecting on this and understand what are the differences with conventional approaches, and also making sure that really the value proposition was to make sure that we make best use of whatever resources are available, rather than trying to go to one extreme or the other. We are not quite yet ready to use 100% IBR system, even in system normal. I want to restore that system. And likewise, there are a lot of IBR currently installed and being installed in different countries across the world, and it's not appropriate anymore to just consider all of them disconnected and don't use them at all during system restoration. So these are the first 2 points that I have in this slide. Besides that, so we're talking about larger scale generation, if we're talking about synchronous generators or inverter-based resources. But we should also be conscious that there is another element, that there are distributed energy resources. There are more in some country than others, but it's becoming to the point, for example, in this country, approximately 20% of installed generation capacity comes from distributed photovoltaic, and each one of them in isolation obviously is very minute and a small kilowatt range, but when they all come together, it's in range of several gigawatts, and they cannot be neglected either. And we're talking about the distribution side and low voltage side. We're talking about generation, DER, but also the demand response that we are seeing, each one of us seeing in our houses, that there are significantly more inverter connected devices than used to be. And all the new trends with electric vehicles and hydrogen electrolyzers, it means that we are moving at the same time with high penetration of inverter-based demand, if you like. Because with system restoration, on one hand is the generation, but those generation are reliant on being fed by loads. And the assumption to date has been that sufficient passive load, like a heating load and like, are available to be picked up. But if they are not available, how that could potentially impact system dynamics during restoration. And one of the other points is that when I started my career more than 20 years ago, there was not really any new technology coming in. Perhaps the most you could think of was fax devices or VSC, or was already there basically. But these days, every year we're coming in, and fundamentally new technology comes in, and I'm referring to more than just grid forming inverters. Obviously, that's one prime example, but so many others, and we really don't know how they behave during system normal, never mind, again, system restoration. And if we don't know how they behave, we cannot translate that into functional requirement, that what we desire from them to operate during system restoration. And last but not the least, in the end, we also doing system restart testing, which has been discussed at length in this technical brochure, but all those tests are not possible for all combination and permutation because of the impact on disconnecting part of the load and part of the system and impact on system stability. We are heavily reliant on models and tools to tell us whether the resources that we have are capable of restarting the system, and if not, how we need to alter, for example, restoration path. And this problem, again, become more and more complex as we are bringing in inverter-based resources into the mix. So, and this is a basically further testament of the point that I wanted to highlight. The key point I want to make from this slide is that we are talking about generation, and generation becoming predominantly inverter-based generation. That's a valid point, but I've already made the point on the DR and load to some extent in the previous slide. The same is happening at the transmission or network level, let's say network level. So we have these three elements that constitute the power system. What we are seeing is not just a system where the inverter-based or power electronic-based resources growing substantially from one element, but they are growing from all aspects, and the interaction between these devices, especially during system restoration, which is a lot less fat is available. So there are only a handful of components, and the behavior of one component, maybe during system normal operation, can be absorbed by other buffers or margin available in the system. But depending on how one or two components or how their interaction manifests, you could essentially upset everything that had been restored until then. I try to simplify this. There's a lot more can be discussed, and I didn't want to basically teach you here about generation technologies, but this is really summarizing some of the key points in the technical brochure, and then Cheryl will take over from me and will add a little bit more on what I have here. My classification of generation technologies are IBR that we discussed and synchronous, and the combination of IBR and synchronous. That is not something that we discussed at great length in technical brochure, but we had at least two examples using LCC, HVDC, and synchronous condensers, and more work has been done in that space, and we have a presentation on Wednesday talking about this, but bulk of our work was concerned about the IBR and synchronous generators. And with IBR, maybe a misunderstanding that currently there, that you have to be grid forming in order to be able to provide these desired characteristics. If you have a grid following wind farm or solar farm or battery, they should be disconnected or should not be utilized. But we are in an era already that these are dominant generations, so we cannot discard, and otherwise the restoration is going to be a lot slower. And starting from line commutated converters, the LCC, HVDC. So this is probably the extreme of least grid-friendly power electronic device that you can see in the power system. But there has been some good work in it from Brazil that has been included in this technical brochure on how to use LCC, HVDC to expedite system restoration. And the advantage that it gives you well before batteries comes in, to have a device that can behave like a load or like a generation, basically. And then what has been mostly focused is on the overall family of force commutated converters, grid following and grid forming inverters, and somewhere in between, and I'm not going into commercial brands, so I don't want to call them in a specific way, whether you call them grid supporting or grid synchronizing, basically grid following inverters with less adverse impact. And these are different applications that we have presented, both in a space of simulation results, but also field testing. Again, unfortunately, we weren't able to present every single result here, but really we want to give you some inspiration if you are interested to read particular chapters of this technical brochure. I'm not going to, again, teach you technology. I'm happy after this meeting come and have a conversation. The reason I'm putting here with grid following and grid forming inverters to highlight that the differences are not as acute as would otherwise be taught. It's really similar structure that you have in any voltage source converter based on back-to-back or even not back-to-back converters basically, but the way that they are controlled and whether you control voltage and current and whether you control voltage or current in the inner loop or outer loop, that matters and determine whether it's a grid forming or grid following device. We have had discussion on impact of, for example, additional fault current, and this is basically an ongoing work that had been done outside this technical brochure. But the key, answer or conclusion is that obviously a lot of things that we are using grid forming synonymous is not necessarily to do with grid forming, but more to do with the storage capability that grid forming devices are bringing in. And perhaps one of the key conclusion is that we cannot restore a power system even with 100% grid forming if there is none of them is based on a storage. So this table, I'm not going through each one of them, but I've just put some as a salient point. Unfortunately, it's recorded, so you can go through and read them. But for some of you, maybe with operational background coming in, I just want to add a little bit more flavor into the differences between grid forming and grid following inverters. And the first two perhaps are some of the most important ones in terms of determining what we need for system restoration, which is the one is the ability to withstand certain system strength. And as we are restarting the system, even synchronous generator is the blackest starter, the fault level available in the system is going to be very small, and how you can bring in IBRs. Obviously, if you use a grid forming or combination of other IBRs to restart the system, that would be different. And the second question is that if you are bringing whatever the source is, a synchronous generator or a grid forming inverters, the objective of system restoration is not to energize a single component. We know that all these devices can self-start themselves. But what then? So the system restoration, as I will show a little bit later, is to do with energizing end-to-end power system, and always the assumption that drives developing system strength procedures, assuming that there is zero electron available in the power system that you are energizing. Okay, so this is a point that I'm building here, and Lalin will take when he shows some of the simulation results. And in my very first introductory slides, one of the points I mentioned is that the dynamics associated with system restoration are much more complex compared to system normal, even in a system with dominant behavior of synchronous generators. And the reason being is that if we have an interconnected power system, this country right now, right here, the types of studies that we are carrying out are primarily the first one, basically, which is on system stability. These are typically lower frequency phenomena. So my book is that anything under 300 hertz, you might say even under 50 hertz, but that's the kind of thing that we are discussing, depending on the bandwidth of the control system. And all these discussions we have had on the use of different types of simulation tools, which I leave all those points for Lalin to elaborate further. So this is obviously a challenge by itself, but then you have to deal with two other challenges, and you have to deal with them simultaneously. So you cannot even deal with a different platform, but that's not what the way commonly done. And those two other issues, one is the power system harmonics, basically, during restoration. And the particular risk is not necessarily what is the total distortion, but excitation of resonances. Again, Lalin will build on that and demonstrate some result. And last but not least is the high frequency transients that in a day-to-day system normal operation, we are not really interested. When we look at power system as a whole, how it responds if the dominant frequency of a phenomenon of interest is 2 kilohertz or 5 kilohertz or 10 kilohertz. Because again, the same reason that there is enough fat that really we don't need to be worried about. During system restoration, these dynamics also would be very important, and Lalin will build on that. Okay, so now let's go and have a few slides on the technical brochure, and then I will hand over to my team members to present different aspects. So we discussed about the drivers for developing and establishing this working group and publishing the technical brochure, which was made available a couple of weeks ago. These are the points that we have discussed in different chapters in the technical brochure. One of the points is the lessons learned from other blackouts. So I will summarize all of them in one slide, but that will not do the justice to those basically incidents. And we try not to just discuss what happened because they have been discussed previously. They are known, but what we could learn from it and what we could apply for our practices, depending on where we sit anywhere in the world, basically. So this was one of the key objectives. And the color coding how I've made here is that this just gives you a flavor of, depending on if it's green, the topics that discussed in this presentation at great length, and if it's red, we haven't covered it. And I should be very clear that this is not based on order of importance. Unfortunately, we didn't have enough time to present. So all these topics are equally important. I'm not by any nature trying to suggest one is more important than the other. And if we basically focusing on such an approach, we just get short-sighted and we won't be able to achieve an optimal outcome. And then the role of different generation technologies that Cheryl will cover, and likewise the DR and loads. On transmission distribution network, we had a small discussion. It's not really greatly covered. That's probably one of our largest chapter, but we weren't able to discuss. Physical testing of the networks, especially looking at the wide area performance, not a single generator. We have many examples for synchronous machines, for inverter-based resources. And the key point is that these are the types of tests that involve multiple components in power system, not just a single element. And there are some contemporary tests, for example, using grid-forming batteries to energize wind farm. And these are real power systems. They're not like microgrid or lab tests, so they're all real power systems. Another very important point is the interface between the cyber and physical system. Everything that we discussed and everything that we have been concerned about is to date on the physical power system, but it's already at the point, and there has been several near misses, that the interaction between cyber and physical system could determine and could have a different outcome on how you restart the power system. And this has been one of our chapters. Unfortunately, again, we don't have time to cover this. And last but not the least, our data models and tools that Lalin and Vikas will present on. This is really, I'm not going to spend too much time because for those of you that have been involved in system restoration, it's not a lot new, but I'm just trying to bring everything together and take it from there and go to the next few slides, basically. Restoration strategies, if you're asking like 5 years ago, it's been the first two primarily, the bottom up and the top down. And the bottom up is the use of dedicated black start generator, basically. The top down is the use of adjacent healthy system. And in this country, for your interest, we have both approaches. For example, in South Australian blackout, the first approach didn't succeed, and the second approach did, and that was the approach that was adopted. Hybrid approach allow you to use a combination of the two. Obviously provide the benefits of the two approaches, but you should be conscious that maybe that's not practical in a real system restoration, requiring much more switching and much more control room staff. And one thing that we discussed very briefly is not widely used, but in UK they are pursuing this quite aggressively, is the use of whatever is available at the distribution system, at least to energize some part of distribution system. So this is not going to energize the end-to-end power system based on a black start capable generator and distribution system, but what you can do with the logic of every little counts and how you can expedite system restoration. So this is a simplified bottom-up system restoration process like provided you for, but this is the most common approach in this country and many other countries to have the assurance that if you require black start, a generator is available and has been tested previously. And what is basically the logic is that if system goes out completely with 0 electron, we would use a black start generator. It could be anything, typically these days or previously, a synchronous generator, and that's to restart part of the transmission network, because that's the fastest way of restarting the power system, and then picking up some other generators, because you want to expedite the restoration, you want to proceed with energizing transmission network, which is the backbone of your network, rather than going into too much into distribution network, and that could be basically a trap pretty much. Once you have done that, then these generators, especially thermal synchronous generators, would need sufficient stabilizing load to be supplied, which is what you would do typically with the larger loads to bring in to supply the stabilizing load. And to be also very clear that the objective at this point is not to supply necessarily load. That's not the priority objective, but to making sure that the backbone of transmission network is supplied. And once done, that can then be going into the distribution network. And as you can see here, everything to do with inverter-based resources is grayed out. This is the typical approach. In some countries, and as we have discussed in the technical brochure, something better is done. It's not quite acute as we are showing here, but this is not too wrong in many countries, which what it means is that a little bit waste of such excellent resources that are available, and maybe we don't know what capability they have. Equally, we don't know what limitations they have, and that's one of the things that we try to highlight a little bit in more detail in this technical brochure. And one thing I wanted to also mention to set the scene, we talk about blackout event, and this not just here in Australia or in secret community, but in worldwide. Sometimes we are using it in wrong context, at least for what we meant and what our focus was. It's not an event that like happened in, as I have examples of, in Australia 2018 or UK 2019 or ERCOT 2021. These are all called blackouts, but to us, none of these are blackouts, basically. So these are load shedding events, for example, in the one in ERCOT. So you don't have fuel available. You can't do anything with it. System is not black. System is completely intact and healthy. But they are very different things. But what we are really talking about and what system restoration is about is that you have lost a part of your system that you have to be restarting, rather than you didn't have fuel to allocate for loads. And likewise, the UK event, for example, yes, it's very unfortunate loads were lost and like trains basically stopped, but this is not a blackout, so none part of the network require a restoration for that event. So we are actually talking about events that we have highlighted 6 or 7, such as in Australia or Brazil or India, Turkey, that they are involved in loss of a large part of power system. Sometimes the whole lost part might be intact, sometimes part of it might be damaged. So these are the lessons learned from various blackout events. I appreciate this small font, and I'm not going through each one of them basically, but this is really put, like I said, I cannot do the justice by, presenting everything that has been discussed in different events. But I'm not expecting you to read basically all of it. So you will have the recording and you will have the technical brochure to go through. Again, the same point that I was discussing earlier. So I'm more interested to convey the classification of types of issue that we need to look at. And that was an inspiration for us to what to be looked at in this technical brochure, which what the classification was. We talk about network, we talk about generation, and we talk about the load. And then an overarching level that brings all this together is basically communication and protection. So communication and protection. So these are the 5 categories, if you like, of issues and lessons learned and what was done in that particular instance. I'm happy if you have any question on particular event to answer, but I would not be spending much time on going through every aspect of the lessons learned. And this was the last slide for me. Like Jaime introduced, I'm happy to take questions at this point. And once I've finished, my colleague Cheryl will take over.
Babak, thank you for your presentation. Can you inform us what progress has been made to develop cranking paths in Australia?
Okay, so I'm actually suggesting that we wait for Cheryl to make presentation. Perhaps then we can answer your question, because some of it will be discussed. If you don't mind to wait until the second part of this presentation, I will not forget your question. I promise.
Hey, Baba, quick question, and I know this might be already there in the TB, but few slides back you mentioned, and I agree with you, that the Australia 2018, the UK 2019, and the other events are probably misnamed as blackouts. And then the next slide had lessons learned from recent blackouts. Could you just quickly talk about, like, give an example of which were the recent blackouts that were considered for those lessons learned? And I understand it might be there in the technical brochure.
Okay, all right. So you're asking what were the dominant events that we consider in this? Yeah, sure. So obviously the one that and I was just talking to Jaime in the morning, so that it's already two of us. So in 2018 in the large disturbance workshop, so I presented about the 28th of September South Australian blackout, and Jaime presenting about the Brazilian blackout. So we had about Turkey, we had about India,
Argentina.
What else?
Argentina, yes.
The ones that we covered though in the technical.
Yeah,
version.
I think it's in there.
So these are the ones we covered.
And obviously the 2003 US blackout.
I don't think we covered that.
But anyway, just an example.
Yeah, sure. Yeah, go ahead, please.
Yeah, so I was curious, do you know what the largest restoration that's ever been done from inverter-based resources only to start? I was just curious if people knew how big of a system. I've heard of like little islands doing single megawatts, but I was curious if there's anything any bigger around the world.
Okay, so very good question. I don't have a definite answer, but we all, because we have the representation from all major TSOs around the world, I can confidently tell you that is under 100 megawatt, but exactly what that number is, I don't know. So there has been, and I'm talking about real restoration attempt rather than someone changing mode on, particular plants in UK basically, and call that, restoration. So there is one that we included, for example, restart of a small distribution connected wind from reforming battery in France, but I don't know exactly what that megawatt would be, but very confidently can tell you it's under 100.
Okay, thanks. Yeah, it'd be useful because obviously I think into the future, people will be trying larger and larger inverter-based system restorations, and there'll probably be a lot of lessons learned out of those.
Yeah, sure. So one thing to clarify, I mean, don't get mixed up with system restoration and black start. I think they are two little separate things. Whatever Babak mentioned was an example of IBR black starting something. It does not did restoration. Restoration involves energizing EHV transformers, lines, and all that. That did not happen, but it was more of a IBR starting, maybe auxiliary load of some non-black start unit and things like that. So
yeah, maybe I can perhaps add a little bit. So basically, these are all predetermined and prepared restoration in a highly controlled environment that you have planned for it for 6 months or 1 year. You know what's going to happen, everything succeeds. Whereas I think what Vika's referring, if a problem happened, whether in reality we can use inverter-based resources, that to be determined. I'm actually optimistic, and in terms of desktop simulation, so I think we have done some work, not as part of this working group, but demonstrate the capability of grid forming inverters. And we have a presentation on Wednesday, basically. So the capabilities are very promising, and I think Deepak and every you guys, because you guys also have done some work. So again, but you have a good point. So these are, either, desktop simulation or fully controlled test environment, rather than waiting for act of God, and then how we can use this generation, basically.
Yeah, my question is that with latencies in systems, that if you are going from a black start, and whether it's inverters, and let's suppose it is for the moment, then subjected to faults or some idiosyncrasy, which is a negative into the system, can protective devices or control devices act to save the situation before it cascades into something because of that latency?
Okay, that's a very good question. So that's basically something that we don't cover basically in this presentation, but it has been covered in the technical brochure. So your question is that obviously predominantly the sources of restarting the power system have been synchronous generators, which provide a certain fault level, and the protection system have been obviously designed based around. And even with basically such an approach, there has been concern, and we have actually presented examples, real examples, that the relay was not able to operate correctly, or basically disconnect the incorrect part of system, and that's with a synchronous dominated power system. So as you go to much lower fault level, so there is a concern that this protection may not operate. With use of inverter-based resources, you could provide the same level of faults, but obviously that come at a cost. And the question is that if that is necessary, or perhaps to rethink this, what types of protection relays we have in power system that are most prone to maloperation during these very reduced fault levels. Prime examples are anything that act based on current, basically, whether they are overcurrents or if they are fuses. And then the next level, anything that indirectly or partially uses current. You have, for example, negative sequence protections that they used in some directional relays. And then you go to distance protection that still uses current, and that impedance might get lost. And the question is, maybe we should consider more the likes of differential protection and other types of protection, because it's much cheaper to upgrade protection than upgrading the sources of generation to make sure this relay operates. But what the problem that you're stating is a very genuine and important one. I agree. Maybe we take one final question and then we move.
Yeah, thank you, Ahmed, PwC, Northern Territory. I'm just interested in what you just mentioned as well about, so you are considering the inverter-based technology more regarding black starting. You're not considering restarting the system, knowing that the main challenge that we have, especially in a small network like the Northern Territory, is the system restart through, creating corridors and energizing transformers and rush currents, and obviously putting stabilizing load on the system.
That's not why I mentioned. I think the response, because my voice is not coming up. So I think the question was that if there has been demonstrated experiences, so the restoration plant is always for a network, is not for a generator. That's why I think what I mentioned, that testing of individual component has been done for several decades. We didn't want to waste our time, basically. So transformer energization and excuse me, all this consideration is part of it. So that's, I think I made myself clear that this is a system to be restarted. If we can, restart a generator 100 times, if it cannot restart the next generator, or like you mentioning, if because the transformer to be energized is too large, or maybe it's too large, but it could have been soft started. So these haven't been understood and not reflected in restoration plan. It could cause problems. So everything that we have done in this technical brochure, that's why it's called system restoration. That's not black start. So we have made good use of the work that has been done, looking at a component individually, but our interest is primarily bringing these together. That's why we are talking about the load. That's why we're talking about DR. That's why we're talking about protection, communication, cybersecurity, everything.
And was that done outside modeling or purely limited to modeling exercise? So have you looked at real-time data?
We have also physical testing, both at the transmission. I believe for transmission system, we have included many examples, but for the work that National Grid has done, and that's the only one that we didn't have a real-life example. They might have done it now, but that's everything else is based on real examples. But that's the point I was trying to make. These real examples are control examples. You're not basically waiting for something to happen and then try to record it, because your recording might be also incorrect. So I encourage you to go and read that. The only one that you don't find a real example is the approach that National Grid in UK uses with DR. Thank you. On that note, we are moving to the second presentation.
Okay, so thanks, Babak. You've set the scene for my slides. Probably covered a bit of information for me as well. So in the next few slides, I'll be talking about the different technologies that have been used for restoration and can be used for restoration. So the black start sources that Babak touched on before as the first source to energize transmission and pick up load have traditionally been provided by synchronous generators. Obviously, they were the predominant generation in the power system, such as coal, gas, hydro, and nuclear. It is important to note, though, that not all synchronous generators are black start or inherently black start capable. They do need to be able to start up without an external supply. Obviously, there's no electrons in the network. So, for example, a large gas turbine that could be black start capable can do this with say, a diesel genset, a cranking generator to start up its auxiliaries, and then the gas turbine can start up. Another important role that the synchronous generators have played for restoration in the past and currently is to provide support to energize lines and pick up load. So even if they're not black start capable, they are a really important part of the restoration process. So as everyone knows, there's a high penetration of renewable generation primarily connected through inverter-based plant, and that has reduced the number of online synchronous generators and definitely the number of traditional black start generators available. And even if these synchronous generators don't retire, they may look to change their operational approach throughout the year. For example, they may be online for part of the year and offline for the other part, which means that they might not be available for a blackout event when it occurs. And this also reduces the number of baseload non-black start synchronous generators that have that important role in supporting energization of lines and picking up load. And that could reduce the load restoration capability. Which may also in turn, unfortunately, make the restoration time a bit longer, as well as the fact that because traditional synchronous generators may not be starting from a hot state, they may be starting from a cold state. That will increase restoration time because you're talking about tens of hours of restart for these traditional generators to start up from different states. So just summarize the difference between, especially in the technical brochure, we cover this, what a black start service is or source is and what a restoration support service would be considered as. So as I said, black start source has to be able to energize its point of common coupling without external supplies to then be able to on its own energize transmission network or distribution network to auxiliaries of non-black start units. And it provides that stiff voltage and frequency control at the very early stages of restoration, as well as fault current that is useful for protection, which is what that person was asking about. The other consideration is that these black start sources have to be resilient enough not to be able to be adversely impacted by other generators and network that are being re-energized during the process. Restoration support, on the other hand, assists energization of lines and transformers in conjunction with black start sources. They can also provide voltage control and frequency control to reduce the burden on the black start source so you can energize other longer lines, as well as provide the much needed fault current and obviously pick up load. So I guess in terms of inverter-based resources, obviously they do need to be considered for restoration going forward. There's a number of considerations that have to be thought of carefully. For example, where are these inverter-based technologies connected? Are they connected close to an existing restoration path? Obviously, inverter-based technologies, renewable generation, are installed at where there's good wind and solar resources, which might be quite a distance from where traditional synchronous generators have been installed. They may also require a lot of switching steps to get to them during the restoration process, which might also affect their ability to be used. The other consideration is their functionality, so the reactive power functionality. Maybe some inverter-based plant have fixed power factor control, which may not be useful for restoration purposes, or maybe they have dynamic voltage and frequency control, which would be useful. And then obviously, importantly, which Babak already touched on, is the short circuit ratio stability requirements. So for grid following plant, that is certainly a consideration. They require minimum SCR and inertia requirements. And we have to also understand their fault right-through behavior through transients that could occur during restoration, which is line energization or load pickup. So this is a real challenge for system operators in the early stages, because we have to understand how many IBR can be supported and in what stage. So we have to understand how the restoration area looks like. There's also another consideration, which is what happens if an IBR is lost? Would we have to rely on the black start source to cover that energy? So is there additional reserve that has to be accounted for the black start? And something that Babak's already covered on, which is the protection, security, and reliability in terms of fault current. Specifically for grid following IBR, the technical brochure talks about use of this technology. It would be great if we could leverage existing IBR on restart paths to help minimize the energy use of the black start source. But it's important to obviously think about when we can actually use them, because they have to be in a location that's obviously viable, close to a restoration path. And but if they are, they can, and the energy source is available, so there's wind and solar at the time of the energization, they can assist with load pickup when other traditional generators have been restarted. In saying that, though, however, there are grid following plants that have been installed, which can also already provide dynamic reactive power control, even if there's 0 megawatts, so that there doesn't have to be wind and solar resources available to make use of them. We could also consider these planned for frequency control if they have that functionality already installed, but obviously there has to be wind and solar resources available to do that. But both of these types of functionality can assist energize longer paths and pick up more load. Simulation studies are obviously required to verify the functionality of these grid following plants, and dynamic studies are also important to ensure that they can ride through transients to restoration, and Lalan will cover that in more detail. The other thing to consider is that just because a grid following plant is installed with a certain features doesn't mean they can't be modified to be able to be used during restoration. For example, firmware settings changes could be implemented, such as automatic gain reduction, which has been used in SVCs. In terms of grid forming IBR, there's different forms. Babak sort of touched on some of that. They have benefits over grid following in terms of the fact that they can operate even at low SCRs and can assist in earlier stages of restoration and can contribute to system strength. There's also that potential for black start to be used as a black start source. However, there's still similar considerations for grid forming IBR, because ultimately there's a renewable source behind that. So where they exist on the restoration path is a consideration. Again, frequency response is a consideration of energy source. And so you might need to consider, say, a battery energy source system along with the grid forming inverters. Similar to grid following, the capabilities and the use of grid forming would be prudent to be studied through simulation studies. In terms of their black start capability and potential, we still have to think about how they could self-start. So even a grid forming plant might still require say, some sort of cranking generator, which could be a diesel genset, to restart their auxiliaries. Another important consideration is these inverter-based plants withstand capability for inrush current during transformer energization. And there's mechanisms in which that can be overcome, such as oversizing the inverter, which can be expensive, or looking at other workarounds, which are soft start energization, is where the inverter controls slowly ramp up its voltage to minimize that inrush current. So just take you through some examples of IVR use. Some of this might answer that previous question partially, and this is all contained in the technical brochure in more detail. In Brazil, in the northeast region, there's a lot of installed wind farms, around 8 gigawatts of wind farms, and the system operator has performed analysis and studies to determine requirements to bring wind farms back on earlier. And they've looked at a minimum restoration area that has minimum SCR requirements at different AC substations to support certain wind farms coming back online and equivalent inertia requirements. And through their analysis and studies, they determined that a minimum restoration area supported through traditional synchronous generators can be available to bring wind farms back up earlier. In terms of grid forming plant, they have been used historically as cranking generators, as I said, to start up, say, a gas turbine. Grid forming BESS, for example, in California in 2017 has started a 44 megawatt combined cycle turbine. So that's one example of grid forming. The other example of a grid forming use in restoration is it being used as a black start source. Whilst Babak has highlighted this hasn't been used in reality and during a real blackout event, there have been control tests of this. The Dalrymple BESS battery has been able to restart the nearby distribution network, and also soft start its own transformers and the substation transformer, and it's done that on its own. Another recent example is a wind farm, a 69 megawatt wind farm in Scotland. I don't know how to pronounce it properly, so Dursalloch wind farm. A subset of those turbines were converted to grid forming, and they also needed a diesel genset to be able to resupply auxiliaries. And then that grid forming was able to start up some transformers, and then the entire wind farm, grid following and grid forming, energized the 132 kV and the 275 kV network. And the tests included soft energization and hard energization techniques, and apparently they were successful. So HVDC links have also been used for restoration. Line commutator converter links, which had been installed in the past, do still require sufficient SCR to operate stably. There has been an example of use of this HVDC link to provide black start capability between the Sweden and Gotland island, but it also uses synchronous condenser on the Gotland side for the SCR requirements. In the Brazilian southeast region, their operational restart plans also consider their LCC HVDCs, which there are 6 of them connecting large hydro plants to load centers. And these plants have got the minimum SCR requirements that need to be met for these LCCs to be operated stably, and consider potentially installing synchronous condensers. Just ignore my comment about not yet being used. Has not had a separation event. Because there has been a recent blackout event in Brazil. Voltage source converter HVDC links do not require a high SCR for stable operation, so they can probably be used in earlier stages of restoration, primarily to act like a STATCOM, so providing reactive power support where not as much megawatts are needed. They can also connect an operational part of the region with a blacked out part of the region, or synchronize restored islands together. And there have been physical tests, again, controlled tests using VSC HVDC links between UK and Ireland, as well as Denmark and Norway. So I'll just, for the next 2 slides, I'll just talk quickly about what's been happening in the Australian national electricity market, which I'm sure everyone knows what that is. Has been a recent overhaul of the system restart regulation a couple of years ago. So historically, as has been the case for other countries, the NEM has acquired black starters from synchronous generators. They are paid contractor services, and they're known as system restart ancillary services, so SRAS. And obviously, there needed to be a change for what Babak and myself already covered, because of the reduced synchronous generation, but also because of the high IBR, not only on transmission, but also on the distribution system, which is displacing or changing the static loads available for grid for restoration stabilization of synchronous generators on restart. So the recent regulation changes was aiming to allow for flexible black start procurement. And what that meant is black starters can not only be synchronous generators, but they can be IBR or combination of facilities that can be installed at even different PCCs. The regulation also introduced a new SRAS, so a new paid service, if it's needed, which is called restoration support, which can be provided again by any technology if capable to do so. And this restoration support can include things like voltage control, fault current, frequency control, a combination of them or any one of them. Support also can come in the form of it being self-starting, so that reduces the burden on the black start source, as well as provides stabilizing loads. So for example, a grid forming BESS to provide load for synchronous generators, or even aggregated DER that is controllable. I'll just go quickly through an example of what restoration support is and why the NEM would procure it. So in this example, it's a made-up example, by the way. This is not a real restoration path. But say you have a black start source energizing a network down to generation A. They both in conjunction then energize the long lines to generation B and pick up load. In that restoration path, there is an IBR there. Historically, we would have ignored that because of SER requirements or other issues. But if generation A retires or is not available for black start or restoration, this black start service may not be able to energize all the way down on its own to generation B. So we could look at then procuring restoration support service from that IBR that's on that path, which could be through a modified controls of those IBR or using their existing functions if they're, say, grid forming IBR. And then in conjunction with the black start source, they can energize the lines to generation B. Distributed energy resources are also important to consider for restoration. There's different types. There's the synchronous generators, the embedded synchronous generators, or smaller synchronous generators distributed throughout the network. There are some challenges that have to be considered for synchronous DER. For example, coal load pickup challenges. So what that means is that the, say, immediately after picking up or re-energizing load, the load profile might not be exactly the same as it was prior to the blackout because you've lost load diversity during the interruption, so say for thermostatic type loads. So you might actually see a higher amount of load than prior to what you would have seen at the blackout, and then it would reduce. So that would impact on synchronous generation governor responses. They're prime movers, the speed of response in terms of picking up that load. Also, some of these synchronous generators are lighter machines. They might not be able to provide a large amount of reactive power range, but can be black start capable. There's also the non-controllable IBR. So, for example, rooftop PV, which can provide some concerns for system operators when restarting the system because they might reduce the load that's required to stabilize the synchronous generators by offsetting the underlying load. They can also provide this destabilizing impact on coal load pickup because the load is varying a bit more differently. In addition, they may also be inadvertent impacts. So say we've picked up the load, underlying load, and the restoration process is continuing. A transient or fault might occur during that time, and you might see IBR trip off because some of these IBR are not capable of withstanding certain voltage or frequency events, and therefore you're losing generation that might be there, and the underlying load will increase, so you're putting a strain on the generators that have been restored. The other thing is controllable load. So you could have a BESS or some dispatchable load on the distribution or distributed throughout the network. These controllable loads can provide a faster speed of frequency response, so maybe less susceptible to cold load pickup, and they can provide some level of system strength and inertia, but this SCR and inertia requirements still need to be thought about, like in the transmission system. They may also have the ability to provide reactor power. That's the end of my slides. Does anyone have any questions?
Chart and Walt Ema. When we talk about black start, we talk about black start paths. And traditionally, we had these paths to get energy to auxiliaries of coal fires
Yes,
to start them up.
correct.
In the power system of the future, we don't have to do that anymore. Have we thought about alternates to that traditional black start path? Because I see you still refer to
Yeah.
a black start path.
Yes.
I don't think we need those anymore.
So
But we also have to consider the amount of people you have in the room to be able to manage all these little islands that you're going to form. Thank you.
Yes, so I think I might need some help from the panel, but one of the things is it's still important to highlight that synchronous generators are going to be around for a little bit longer, and they are needed for restoration. Unfortunately, we just don't have that ability yet to transition straight into no synchronous generators. And if we need synchronous generators for restart, we need to restart the auxiliaries. In terms of the smaller islands, I don't believe we really consider them, except for the National Grid Distributed Restart Program. They have done a lot of work in looking at restoring distribution, restarting from the distribution network and building up so smaller islands. We sort of touch on that in the technical brochure, but don't go into in great detail. But yeah. Oh, I don't need that.
Good to see you, Charles. I haven't seen you with long hair.
Everybody says that.
Okay, so two good questions. So the first one, I think on coal-fired stations, at present, I guess we have to pick them up because if they're not picked up, then they are basically cold, and picking up a coal-fired station cold may take like 48 hours or 72 hours or, better than I do. So that's the challenge. Once they've gone, maybe we have better opportunities, but even so, I think we're talking about like grid forming inverters. When coal-fired station gone, you have hydro units, you have gas units, give you a little bit more flexibility. But I guess even then, it comes basically the question that if we have a lot of grid forming inverters, if we're using the grid forming inverters primarily to provide inertia, or maybe we use those synchronous machines to give us those inherent characteristics, because with grid forming inverters, they are current limited devices. So they have all these capabilities, but it's also an optimization and priority, how other services could potentially be optimized against something else that would naturally coming from hydro units, which going to be there for much longer. On the last one, I am exactly with the same view as Cheryl, that basically, synchronizing those small islands, haven't been considered. And I think that's probably more of answer for it, like some yourself and Jaime. I would actually, that's my view, and I don't mean to be cynical. Maybe in 5 years' time, we completely wrong, but that probably become a distraction also. How many staff do you have to synchronize these tiny islands and bring them together? That's my view. Obviously, working with you previously, to me, it's a distraction. I'm happy, Jaime, if you have a different view. Okay. Did I answer your question?
Thank you.
So I have the mic, but I have actually a point regarding auxiliary load. So I don't know if if you want me to take this offline or just say it out, because I have a point regarding the auxiliary load that you mentioned. So it's not that inverter-based resource plants will not have auxiliary load. They have a lot of cooling load. They have air conditioning load. A battery container has an air conditioner put in front of it, and those air conditioners are motor loads. So that would have to be picked up first. So there's still some amount of auxiliary load to be picked up, so which the cranking path would have to go towards. There's also some aspects of onboard inverter power supplies that need to be charged up and so on, which might still require some auxiliary load because the DC capacitance has to be charged up and things like that. So the nature of the auxiliary load will also change in the cranking path, but there might still be some amount of auxiliary load to be picked up.
Yeah, maybe I can take that. I don't disagree with you, but I think the point to consider, everything you said is correct. Perhaps what we need to consider is the ratio, basically, that if you have a coal-fired station, you're talking about, at least 8, maybe like 15% of load pickup. And unfortunately, the bad news is that is older power station, everything is direct online start. So you don't have any VFD or anything like that. With battery, wind, like everything else, you are correct. There is auxiliary. We can't say that there is non-auxiliary. They will be picked up by themselves. But the thing is that, first of all, they are much smaller. So my rule of thumb is 1%. So if you're talking about 1% to 10%, I guess that's, to me, the difference. But I think you're making a good clarification that, yes, there are auxiliary rows, and it's not like everything will happen by itself. But it's fair to say that it's much more straightforward than energizing it, significantly, especially coal or nuclear-based. Nuclear, which is not involved anyway, coal-fired-based station. And like in Australia, I'm sure elsewhere in the world is similar. That the bad news is that these coal-fired stations typically in very similar area, which is where the mines are. So you're not going to pick up one of them. You're going to pick up many of them. But with IBR, you get a little bit more diversity. So hopefully I answered your question or comments.
Sorry. In the examples where grid forming batteries have been used in cases, how is storage managed, and are they only restart providers? And do you see an opportunity to revise our pathways again to pick up loads that may be actually putting power into the network from the distribution level?
So sorry, did you say grid forming or grid following?
Yeah, sorry, grid forming batteries.
Yeah. So I think in the technical brochure, there were smaller applications of grid forming being used to restart the network. Sorry, what was the second part of your question there?
Like where we've reviewed paths to avoid high DER that might push or have really low load.
Yeah.
Do you think there's an opportunity if we have grid forming batteries that can kind of go both ways
Oh, yeah.
to actually pick up those reverse or power injecting areas?
Yeah, so the technical brochure probably didn't consider that in too much detail, I don't think, but definitely in the Australian regulation, we are considering various different forms of use of BESSes. Obviously, energy storage BESSes can provide the megawatts and other functionality for that reverse type of bringing a load or providing megawatts. But in terms of the examples in the technical brochure, they've been been providing reactor power and megawatts. Yeah.
Maybe I just add one point. So yes, the short answer is yes. So if their batteries are in a strategic location, that would mean that you need to alter the way that you're restarting the system. It should be done. But I guess one thing should be considered with batteries. I mentioned it briefly. Yes, they have all this capability. And of course, they are a storage, but also we need to be conscious that the storage is only for a few minutes. So how to use it most, judiciously. So it's almost like a single shot. You have to be using it to achieve something else. So it's not the device to use it basically as a sustained load, but essentially looking at the long term. So that it's more a means to an end. And that's with the current capability. Obviously now there are for our batteries in Australia, they have already been for many years in like US and other countries. But this is the reality of, yes, storage is great, but currently with lithium ion capability for long, and sustained operation, especially looking at blackout and system restoration, is not quite there. So I'm actually suggesting that
One last thing I want to add is, so even in US, sorry about that. So, I mean, it's also economic decision as well, because, like in US, there is a requirement that if you are a black star resource, you have to carry that capability at all times. That means you cannot use battery for that particular capability. So it's again an economic decision as well. So
thank you. Okay, and I promise I answer the question. Was gentleman here? Are you still there? Okay, so you asked me a question about the restoration path. I think that's already come a few times. And the first answer I can provide you is done very differently in different countries. I can share with you how it's been done in this country, and there are people from the National System Operator, AMO, including chart that runs the control room. We can ask more details, but the process very simply is a non-market service. Everyone that believes they have the capability submit expression of interest to AMO, which is the National System Operator, and they basically have a EMT system model of their regions based on the level of detail that required to assess system restoration. And depending on which sources are successful or unsuccessful to deliver the capability that AMO is obliged to procure as per system restart standards, and depending on their cost, they will decide which combination to procure. And which brings us nicely to the point that Lalin is going to discuss on using EMT simulation, and that's the most rigorous way currently to decide which sources, already allocated sources you need in the system to succeed with system restoration. And if you need more questions, I think we have 10-15 minutes at the end to basically go through that.
Thank you.
Thank you.
Okay, good afternoon, everyone. I think Babak can give you some insight to the restoration techniques and the IBR involvement. So let's go quickly to with some of the studies involved in the backstart restoration process. It's doing the same thing. Okay, yeah, thanks. Yeah, obviously, the black star situation is completely different from the normal system condition. So therefore, it is very important to do a study and make a confidence about the restoration path. And if some mitigation options are required, you have to implement them. I mean, in the case of simulation point of view, and make some justification that the restoration process is kind of a secured one. So once come to the general, I'm mostly talking about here the general studies, the studies in all the general tools. Obviously the RMS studies, phase domain studies, then EMT or electromagnetic studies, and also the real-time simulation studies may involve with any study with the backstart restoration process. Once come to the RMS studies, we know that obviously this is very common, and the people heavily used for the load flow analysis and some system stability. The main advantage of the RMS studies is simple, and you can apply for a relatively large area, but there's always compromise to the accuracy and not reflecting some of the phenomena I will talk behind here, like inrush current and possible resonance condition and some of the induced voltage will not be replicated in RMS background. So that's why the more detailed EMT studies may require. They produce the, as you see in the right side, the instantaneous waveform with the more details. Obviously, you will see more information like inrush currents, transient voltages, and some other things. But again, the restriction would be it's more detailed, and you may not go with very large areas. But with the recent development especially in EMT area, the simulation areas, I'm not thinking once come to the black start, relatively small. Now it's almost possible to do any kind of study in EMT background. But it's not the case if you talk about 5 years ago. Real-time simulations, it's give you obviously more insight because you can engage with the hardware in loop with the actual controllers and the protection relays. But the limitation may be most of the time the replicas of these protection relays or control system may not be available. So if it's a new project, yes, probably, but backstart is kind of, you're dealing with the existing equipment in this power system. So it's a huge challenge. Under black start condition, obviously we have few generators, means the short circuit level is low. So I think many of you heard about under low short circuit conditions, you may have many problems, even getting some IBRs into the system. And less loads obviously cause load damping for high frequency transients. And also the light loaded lines will make heavily the voltage issues, line charging in other words. So therefore, I mean, these are the few things we have to understand before we do a study. This is the basic conditions of the black start, small black start model. As time permits, I don't want to talk about many topics, but let's concentrate on EMT studies, because there are a few things that we can highlight through the EMT studies we cannot be seen in the phase domain simulations. The examples are mentioned here, like line or cable energizing, transformer energizing, obviously unbalanced faults conditions. Some of the dynamic load pickup, but can be seen through the even the RMS software too, and obviously resonance conditions. And the last point, I think very obvious for you guys, they must come to the IBR. If you want to have a good insight, the MT is required. Let's go through a few of the examples. Once comes to transformer energizing, there can be, depending on the size of the transformer, heavy or high inrush current can be 3-4 times the rated current. Could cause, if you not choose particularly size-wise a smaller generator, and if you have a relatively larger transformer, the generators could trip due to overcurrent, unless otherwise probably you are not having a harmonic blocking or some other schemes. Or even, I mean, with that, there's a possibility. And also due to these inrush currents, you see the bottom waveform as you see the EMT simulation with the inrush current, and the top waveform is the voltage, the RMS voltage. There can be a drop on the voltage, which may cause some load tripping. So that's some annoying part during the black start restoration process. There are a few solutions already. Maybe you guys are aware about soft start, and I'm not going to detail these kind of things because I don't think we have enough time to talk these things in detail. And point on wave switching of the transformer, energizing the transformer. And another condition during the transformer energizing may lead to have a system resonant condition. So what is really happening here is during the transformer energizing, it throws a large amount of harmonic current, especially second to fifth harmonic current. If you have according to this equation, if you have the second, fifth harmonic network impedance, very large impedances, that can lead to have a very large voltage deviation, voltage distortions at the transformer terminal bus. So as you see here, the bottom one is the inrush current, the top one is the bus voltage. So as long as this is kind of can lead to a sustained situation where the voltage condition can push the transformer into the saturation region, and it will draw more currents, and more current can cause more voltage distortions, and sometimes it may take a bit long time to damp out these kind of oscillations. One interesting phenomenon is called sympathetic inrush. If you heard about that before, simply what's happening, this happens once you have two transformers in parallel, provided that the first transformer is already energized and you're going to do the energizing the second transformer. So during the energizing the second transformer, the inrush current could lead to have some voltage distortion on this bus, driving the already energized transformer into saturation region again, right? As you see here, the top one is the second transformer, the bottom one is the one already energized. It is getting into the saturation region and can draw some inrush current. So this is called sympathetic inrush. That's also a possibility. And another thing you can see through obviously the EMT simulation is the the effect of the unbalanced faults. You know that during a line to ground fault, the healthy phases can reach to in a completely a delta system 1.7, but 1.7 something. But most of the effectively, sorry, yeah, even a effectively grounded system, you may see some kind of voltage there. The problem, real problem, maybe during a black start process, the current is smaller relative to the healthy system, and the protection system may take a little bit longer time to identify the fault current and trip it. And this is causing that the healthy phase is having the temporary voltage condition for elongated time. So we have to be careful about that. Whatever the equipment on healthy phases is having enough TOV capability, a temporary voltage capability, once you have this kind of condition. The high frequency switching transient is another thing, but definitely these kind of things will be done during the normal design stage. I'm not thinking this will be a big issue for black start restoration process. We always expect people have done due diligence during the design stage, and they sized the surge arresters, and they evaluated their switching transients or SOV properly during the design stage, even under very low short circuit conditions, which will give you some protection during the black start process. But I just mentioned here. But the thing is, if you have very large transients, they may stress on the insulation, as well as if you have a surge arresters, sometimes it can be a burden. Energy point of view, it can be burden to the surge arresters. Another phenomenon is this is induced voltage in parallel lines. It's called, some people call parallel line resonance. This could be, sorry again, wrong button. This could be when you definitely have a long line with equipped with line reactors. When you have two circuits together, there can be some induced voltage on the de-energized line due to the coupling effect with the already energized first line. So how it happens is this: the capacitance of the transmission line and the reactor will give you a shunt reactor will give you a nice LC circuit to oscillate. If this natural oscillation, LC oscillation of this circuit is close to 50 hertz, not the case. I mean, power frequency is not the case, because when you're doing proper design, it shouldn't be happen. But having said that, I have to remind you, it's happened a few times in power system. I'm not saying that exactly 50 hertz, that's a disaster situation, but if it's close, you can see that the induced voltages on even though the second line is completely de-energized from the both end, it's just a capacitance, and the inductor can induce very large voltages on the same line due to the coupling from the first energized line. The load pickups like motor start, and these things can be studied definitely in RMS or phase domain software too. But I have highlighted if you can do in EMT background too, EMT tools too. So they're a little bit longer elongated time, the under voltage conditions. So you have to be aware that the other loads, surrounding loads, won't trip due to these kind of conditions. The voltage drop is not, or they're within the limits. So another interesting phenomenon is the ferroresonance. It's needed 3 conditions to be satisfied. You should have some saturable reactors, very possible with any transformer in the power system, and you should have a capacitor. It can be a cable connected to the transformer, and then you need a single pole operation. I mean, out of 3 phases, the unbalanced, they should operate a couple of phases closed, other phases open, or kind of condition. So this I'm not saying this always, that this could lead to a ferroresonance condition, which is very, it could, lead to very high voltages. And it's not a good condition for the system, because provided that under black start conditions, you have very low damping, you have very less amount of loads in the system. So therefore, there can be some sustained ferroresonance conditions you may not see in normal condition. The last point I want to talk about is the zero missing. I think most of you guys are familiar with what I'm talking about. Due to the generator operation, you know that the generator is quickly moving from subtransient to transient to the steady state impedances. Due to that, your short circuit currents become smaller, and if it's happening a faster rate than actual DC component damping, you may see that your current waveform may not cross the x-axis. In other words, it may not get a zero. So if that's the case, even though your protection systems, due to some reason, give the command to the breaker to open the breaker, so practically breaker would not be able to interrupt the current, because the breaker needs a natural zero crossing to interrupt the current. So this condition can be happen. I'm not thinking it's very common with the generators itself, but the combination of cable and reactor in the power system restoration path could lead to this kind of condition. So with that, I think if I summarize, honestly, with the time permits, we cannot talk about much more on all the studies, but this only on EMT studies, which is only visualized through EMT studies, not in RMS background. If I summarize what we talked about already, the obvious EMT studies provide a better insight to some of the aspects we talk about here. It will cover the high frequency transients, and also it will reveal any resonance conditions. They are due to induced voltages, and also obviously once come to the unbalanced situations like unbalanced faults, the EMT would be a good software to simulate. And this is the black start condition you can consider as a low short circuit ratio condition, and once bring IBRs into system, obviously it's better to do some kind of EMT studies to make sure that, especially even with the grid following, they highly rely on the sinusoidal waveform. We are having clean waveform to proper operation of the PLL. So therefore, it is better to have some insight through EMT tool to get a better insight of the IBR, usage of IBR in the restoration process. I think I a little bit rushed through the slides and studies because of the time, as time permits. We have only around 20 minutes, and there's another presenter, but I would like to take a couple of questions.
Yeah, I want to refer back to the slides 32 to about 36, I think they were. And I don't want to be an alarmist, but if you stop on the transformer energization and let's not go forward, but I'm talking about if you've got a lot of inverters which have also got their own voltage protective inbuilt software, or I'm just concerned that with voltage spikes, which you then have had caused by LDIDT type issues, and into transformers, you could have exactly this, and you might even then get some harmonics coming out of it. And I'm worried that, or thinking, and we can take it offline later, that these voltage spikes can knock out the inverters or take them out of operation. And if you've got millions of inverters around a system, you might have a calamity. And happy to talk a bit more about it later on.
Yeah, I think Babak also has some comments on that point. I think, yeah, that's yeah. You want to comment on that? Okay, yes. Yeah, That's a possibility. I mean, the voltage spikes, and then that once come to, you have to be careful on that. The simulation and the real life. So and possibility that some of the voltage spike, maybe some of the inverters may see as a not desirable condition and it immediately trip them.
Let me just add a little bit more in, and some of you might know of me in the audience here. My name is Peter Tyree, and I know a little bit about transformers. And I'm thinking that with transformers, you put in surge diverters and you put in other protective things because the value of the asset is worth it. Would you ever really contemplate putting in a lot of surge diverters or protective devices on low-cost inverters? And that might compound the problem even yet again. Thank you.
Just want to mention, it's a fantastic question, but it's prime candidate for during drink. I promise that it's not going anywhere. I apologize to interrupt. Lali.
No, that's okay.
So, and any other questions?
In thinking about system restart studies and the challenges that were talked about with distributed resources, particularly the non-controllable many small devices, to construct a model to represent the behavior of those distributed resources, what would you see as the really important elements that that model would need to represent to be useful for a restart study?
Yeah, I mean, yes, it's a very good question. Honestly, yeah, there's no any slides on that part here because we confined to the traditional studies. But having, I mean, this question, it's depending on, I mean, if you are really using your DRs on the restoration process, definitely this will be a big challenge to model them correctly and include it in the restoration studies because some of them may not have good models to represent. Even you have the good models, there are so many numbers in different places, and combined with this study will be, I'm thinking, be challenging. And once come to the this process, I mean, it's still, I mean, using IBR in the systems restoration process still in the studies and still in the conversation, and how we do that. I'm not thinking I can give you a very good answer for your question, but though it's a good question. Yeah.
Okay, thank you. So that's.
I mean, I would say, like, while I'm here is maybe aggregate them and at least have their trip settings modeled correctly, because operators do rely on loads as stabilizing load for load generation balance and voltage control, and if they trip, they lose load effectively. So I think those kind of, I mean, load changes, so they cannot control properly. So I think that's probably, I would say, at least one most important setting you should capture. Yeah. So looks like I'm the last man between you and the drinks. So we'll definitely try to be on time. And Babak has told me to give 5 minutes towards the end, so that gives me even less time. So that's okay. So all of these guys covered, the drivers and motivation. One thing I want to point out, these black start restorations are very unique capability. Something you should always have and hope never to use it. So that's big part of the uniqueness in terms of other services which you get from other resources. And also the hands-on experience may be lacking. I mean, you may have more experience on normal operations and things like that, but these are some rare events. So operational experience is literally, almost negligible. And that's why whenever we have a blackout happen, we always try to learn from somebody else's mistake, which is fine, but that at least that helps. So all of the, what Lalin was showing was more, like focus, EMT, cranking paths. But with this changing generation portfolio, somebody has to take a very holistic look at the system. So when I say holistic link, like with this changing generation portfolio, I should know, okay, what are the optimal locations of my new black star resources? What are the sizes I need to be using? How can I incorporate risk in black star resource planning? How can I plan redundancy in my system? How can I navigate through different restoration strategies with different operational conditions. So all of these needs to be answered, especially we are not there yet where we are using 100% IBRs and we'll be using them for black start, but we are from a transition phase from moving from synchronous to IBR system. So these things are still very valid in the system to address. So some of the planning tools which I'm going to talk about next actually focuses on that. So one big disclaimer that these are just few of the representative planning tools, not the only planning tools which you can use. So we try to collect some of them, based on, participation in the technical brochures. Some of them will be presenting here. So first one was from National Grid ESO, where they use Monte Carlo based investment decision making. So what basically they have done, they trying to incorporate probabilistic approach, risk-based methods in restoration planning. So looking into, okay, if I have restoration path, and if I run it through different operational conditions, scenarios, dispatch, human, weather condition, forecast, whatever. So what is the probability of that path to be not viable? What is, if it's a very high risk of that path to fail, then I can basically have some investment decisions right there to reinforce and make sure those paths are viable. So that's one of the planning tool which was used. The other one, again, these are the next one are the one from EPRI. And, as during early stages, the main philosophy or main goal is to reestablish your transmission and generation skeleton. And these are the principles on which these two tools were based on. The first tool is optimal black start capability. So it allows you to take a very holistic look at your system and try to maximize generation capability as soon as possible, and also try to minimize the pickup of critical load, so that once you have generation capability available, you could be able to start your load restoration process. So that's one of the tool, and a very simple application I'm showing here. If you see in the plot, if you start increasing a black start capability at a given bus, after certain increment, you will really not gain too much in the restoration time. So that is one of the similar, like, basic simple application you can use this tool for. You can use this tool for also looking into, okay, if I have multiple options and if I'm looking to identify new black star resources, what is that least cost set of black star resources which I can use, and how many do I need? If I have bids coming in from 10 different regions or 10 different developers, what is that minimum I need from my system to meet my restoration objective? So that's one tool which can help you identify that. Other one is System Restoration Navigator, and that's more of a, I would say, operational planning and operational support tool. One of the big challenges when you're trying to identify new restoration strategies is to how to sift through these multiple combination of network scenarios, generation, and different conditions. So this tool can help you, guide you in that process, looking into, based on where I am on my current scenario and current restoration scenario, what is the next best step to take? So it's basically an optimal cranking path selection tool, so that can also help you not just develop alternate strategies, but also can help you plan redundancy in your system, which we have seen it's a very important thing to have in the system. So those three were the sort of planning tools to help you do restoration planning. I want to talk about next slide on tools which are available to operator. So one of the thing is which can be used is wide area measurement systems, especially PMUs. So PMUs can help you in various stages of restoration. It can help you looking at system assessment, what has damage, what is available, what is not available. PMUs can be used to give you more situational awareness when you're trying to reestablish that transmission generation skeleton. And PMUs can help you when you're trying to pick up the load, and can really monitor frequency and tell you, where to, how much generation you should have to pick up how much load. So just give an example. During I think it was a few years back, Hurricane Gustav, which happened in New Orleans area. The PMUs were actually used from island detection, from load restoration, that perspective, and we have mentioned details in the technical brochure if you want to see how they were used. The other tool, which is control like operators have, is the dynamic security assessment. As you know, like currently vendors are providing that capability where you can save your EMS snapshot and run in almost near real-time scenario to look at dynamic performance of your voltages and rotor angle stability and all that stuff. So that's one option the operators have. Another one we are hearing a lot more is about digital twins. And digital twins are more like advanced DSA, looking into, okay, how can I virtualize and model my system? How can I analyze and optimize my network? How can I monitor and predict what's going to happen? And last but not least, how can I automate and control? So all that is part of now this evolving technology, or what we call digital twin. So that's another tool available to operators. And last, Lalin also mentioned real-time simulators. So if you have capability, if you have computational power, and especially if you have a lot of inverter-based resources, then nothing like capability of doing fast EMT simulations. So with that, actually I give you 10 more minutes for questions. So, but not just 5. Yeah, well, I can answer all. Yeah, go ahead.
Yeah, thank you. Actually, it was really short, good presentation.
Okay.
A lot of good points. My question is on the previous 2 presentations. You guys mentioned on the first presentation about energizing transformer and lines. You talked about 2 methods. One is oversizing the inverter, which is expensive, and then you talked about soft energization. What's your thought, or have you considered in your study the fact that sometimes you can soft energize the first transformer, but you have another long transmission line and another large transformer before you even reach the stabilization load, which means you are forced to hard energize the line and the second transformer. Obviously, you'll be either left with the expensive option, or what have you thought about other options in that scenario? Because soft energization become redundant or not.
I will take that question, but can I ask perhaps first take the questions?
Yeah, I mean, I can answer that too, but Babak, you are feel free to answer.
I just want to make sure that
Yeah.
the opportunity to answer questions. So I just take this.
Oh, I thought you were going to take the question.
No, I'm not taking this at this point. Good question. I will answer it at the end, but I want to give the opportunity for people first ask question directly to Vikas's presentation.
It's not for Vikas.
Okay.
The question is not for Vikas. That's
Okay, but I can try to
waiting
answer if
for-
you can ask.
Ask it anyhow? Okay, I'll ask it anyhow. Okay. This is probably a tangent question. All these restoration studies and the method assume system normal most of the time. Okay, assumes that the network is intact, you got all the lines in service, and you start energizing it. When system goes black, most of the time it's like a havoc. You got number of lines out, or you got a hurricane coming in and bushfire coming up, we're taking a lot of generation out. So what's your thought of the panel about these 2 parallels, where on one side it's a blue sky scenario, slightly blue sky, and on the other side, the real system, when you really want to restart, it's totally different than someone thought. It's probably a philosophical question.
Yeah, so I would say I will not there is no silver bullet which can solve everything. So it depends on how good your situational awareness network is. Either it's coming from PMU, whether you have drones which can go and tell you, okay, what is my system state, what lines are damaged. If you have lost SCADA, do you have functional observability in your system? So obviously it really, but also you need tools which can, well-established cranking paths, they are fine because you practiced on them and you can energize them if they are viable. If they are not viable, then you really need some operational tools which can guide you based on your operating conditions. What is the next best step I should take in my restoration process? That means whether you can have whole digital twin which can mimic that condition, or you can have some operational support tool which can guide you in that process. So again, it's just combination. You need good situational awareness. Also, you need these decision support tools which can guide you through that process. So if that helps.
I have seen all traditional approach here. In the future, black start will be very different. Maybe, hopefully, they will not be black, so black, because with a lot of distributed resources and active portions of distribution network, we will have a lot of islanded operation possible. This can help a lot, but it's not straightforward, but it has to be studied, the restoration of the network. I understand this group did not consider this. Maybe can be some recommendation for future work, or did you analyze it also?
So I know we are recording and I like to coin this term, but don't take me on it. But I always think the future could be more on transmission guided microgrids, which, just operator have more visibility on the microgrid itself and how they can then reconnect and reestablish the whole system. But again, we are not there yet, but maybe one day. Yeah. There's one more question there.
Hi. You mentioned the loss of SCADA before, and actually that's a big one because the communications grid has changed as well.
Yeah.
And we have found that recently, even though we can't get the same SLAs from, Optus and Telstra and those guys that we used to be able to get here in Australia, they simply cannot give us that because it's a different way that network is established. So considering that, do you take into account those cases where you actually might have less than 10% of SCADA available to you? How do you then do your black starts?
So I tell you, and we had that, and I think we decided to take that out in the technical brochure. So ask Babak. But anyway, so we had a lot of work on loss of SCADA coming from, if you completely have a societal loss of communication, how you can gain situational awareness of your system. And if you have partial loss, how can you gain situational awareness? Especially like if you think about state estimator, right? If you lose SCADA from a certain region, and if you have not good bad data detection techniques, your state estimator will start diverging. And suddenly you are sitting there for 15 minutes without any observability of your system. So there are techniques which being developed, recursive approach and resilient state algorithms which can help you identify that area and isolate that area so that you can still get an unbiased solution for the rest of your system. So again, so Babak.
Thank you. Okay, so no, all good. Thank you very much. That's fantastic. So I will take one more minute. I need to answer 2 questions. I haven't finished. Thank you. So the question that Nilesh asking, and especially the one Karen asking, so I guess this was discussed in the working group. So we have 2 things when we talk about blackout and system restoration. One is that basically a sequence of events that we can never predict happen. And basically how you could potentially break the causation chain to avoid that or to minimize the impact. I think that's what both of you talking about. And I'm not undermining its importance, but I guess what we are looking at, whatever it happened, it was act of God. You may predict it better, but you're never going to predict it, every single instance. So what the focus is, we are not here to create more resilience, to break the causation chain, but you are in a system that you have to restart the system. How you can basically restart the system. And part of that is that the cause may be act of God, natural disaster, or the cause of it may be cyber attack. So that was the focus of it. And I should mention that this was also recommended by one of your colleagues at AIMO. It's not me, I had left by then to AIMO, so that was the view of working group. So now I'm answering your question on basically transform energization. I don't believe oversizing inverter is a fantastic idea. So I know it's been done I'm not for that. That's my view. Second part of your question, how you should be tackling that question. To me, system restoration and blackout is a community service, so everyone should be participating in that example that you're mentioning, and it's not imaginary. At least I know one example. So yeah, so at least I know one example in the region that I work. Basically, in that case, you need to interlock all breakers. So basically, you should be avoiding hard start until very last point. So obviously, that needs a lot of pre-planning involving both generator and network side. But you need to make sure that you will soft start it until the point that you can afford, because if you're soft starting, and that's the first question you're asking earlier, you can restart the generator another 2 million times you do it, it will succeed, but it cannot go to the next substation that negate the purpose. So, and this is again the point that you're trying to also make. This is a collective system-wide capability. It's not a generator capability. The limitation may be somewhere else, and how you're going to bundle them together, essentially bringing a generator from a black box, not blackout, black box source to a system-wide source. And that's my answer to you. I believe we are at the end of this, Jaime, if you want to have any concluding remark.
Yes. So this one, I need this. Yes, really, I need this because you are fantastic. Sigrid people and study committee C2 people, you are fantastic. We give you the challenge and you perform the task perfectly. Is Frank with us? I'm not sure. Franco, I'm sorry, you are not the prize winner. But I'm sorry too, Babek, you are not the prize winner. We don't have a prize. But we need to thank you for those great tutorials we had this afternoon. Thank you very much. Congratulations, you gave us a perfect tutorial. Of course, Franco, I said you this before. And thank you very much, Babek, and the others. Cheryl, not really you, because you remembered me about the Brazilian blackout we had 3 weeks ago. I am in Australia, I'm trying to forget this. Okay, thank you. Just kidding, it's real. Congratulations. And I hope you have enjoyed this afternoon. And remember, Study Committee C2 will be again with you next Wednesday and next Thursday afternoon. Do the whole Wednesday, the whole day, and Thursday afternoon with the papers presentation. Thank you very much. Let's have a welcome reception and welcome drinks now.